issue here. Going back in time. Now, just remember, all the techniques of integration that we've gone through now, right? We're all just so that we know how to take antiderivatives, right? Without us knowing like why. So we're shifting gears. We're talking about something else right now, and then the antiderivative is going to come into play. But the area problem is where this all stems from. The area problem. So the area problem was something that had humans stumped for a long time, all right? As we evolved and became more intelligent, we all came to grasp with the idea that we could find the area of a rectangle, right? We could define it, it made sense, right? If this is a rectangle, we want to know what the area is, then all we really need are these two sides, right? Whatever this is, I'll call this width, and I'll call this length. And then we all were comfortable with the idea that the area, that concept, is just the length times the width. And we're happy, right? Yeah? All right, and then we said, okay, well, what about something more complicated, like a triangle? Well, we figured out that there's a way we can find the area of a triangle, right? If we know what the height of the triangle is, drop a perpendicular, call that h, and we know what this is, let's call that, what do we usually call it b, right, for base. If we know the base and the height, then the area we could calculate, and we all agreed would be 1/2 base times height, right? We're all comfortable with that? Are we? Yes. But as humans, the reason why we are comfortable with this, what we did was we took this and we said, right-click copy or Control-C. What's copy? Control-C? Control-C copy, and then Control-V paste, yes? Make a copy of this and rotate it around. Okay, so basically there's the same picture I just drew, this one, but I made a copy and turned it, yes? And now what I'm going to do is I'm going to cut, with scissors, I'm going to cut this little triangle off and put it right there. And what I've created now is a rectangle, yes? And what's the area of this whole thing? Base times height. But I made it out of two triangles, so I need half of that. So half of the base times height is the area of the triangle, right? So can we all be happy with this? Yes? Okay. And then we said, all right, well, let's get more complicated. Let's try that. Why would we do that? Because I have land. This is my land. And that's your land. And this is our property. This is my line, right? You stay on your side. I won't mess with you. Don't come take my shit. I'm not going to take your shit, right? That's, I mean, humans, that's the way we are, right? This is mine, this is yours, right? So we needed to be able to do this and define property lines, areas. I mean, this is what we needed, right? So how do we do this? Well, we could just cut it up. Oops, that's supposed to be a triangle. Sorry, triangle, triangle, there we go, one more, triangle, boom. So I've cut that complicated shape into multiple triangles, right? And then I could go figure out how to calculate the area of each triangle using this idea here, right? And that I could do for pretty much any polygon, right? You give me any number of sides, I should be able to do this, right? Not fun, but it can be done, right? There's no general formula for it, but I mean, I could just attack it and it might take me a while, but I get it done. And then we were faced with the big one, the circle, right? Now we have a problem because we don't have straight edges. And since we don't have straight edges, we can't use the triangle, we can't use the rectangle, right? We have curved parts to this. And so this stumped us for a long time. We couldn't figure out how to do this, right? We all know the area of this, right? We all know that if you can measure the distance from here to here, call that r, we all know that this is pi r squared, right? We all know that. And we are happy with this But they weren't, okay? They, meaning us, a long time ago, couldn't figure that out. We didn't know that that was a formula. So how did we come up with that formula? We will prove that formula in this class. We will prove it. We will show that that formula, where it comes from later, all right? So we're acting right now like throughout history, we were successful with areas until we got to this problem. And the way they finally kind of like got around it is the Chinese were the first one to do this. The Chinese said, you know what, let's just put a bunch of like squares and rectangles inside the circle and add up the area of all of those, right? Just draw a bunch of squares and rectangles inside the circle. We can add up all those areas, right? And if we do that, we'll get an approximation. The problem with the approximation is that it's going to be a little bit short, right? It's going to be too small because you're going to have all these little corners that you weren't able to get, right? So you're going to have some error, right? Error, E-R-R-O-R. You're going to have some error in there. But the better the the better the rectangles were drawn, the more of them I can squeeze in there, the closer and closer I get, right? And so they called this the method of exhaustion, because it was actually very exhausting to actually try and do this. But the Chinese spent years and years doing it, and they got it really close. They were able to say that the area is approximately 22/7 times the radius squared. They were able to get it pretty damn close. And if you get 22/7 on your calculator, you'll see that it's pretty close to pi. What is it? 3.1428, and pi is like 3.1415. So they had it within, 2 decimal places of the true area, and for a lot of purposes, it was good enough for what they were doing like thousands of years ago. All right. So this approximation, it got better and better with time, but it wasn't until calculus that we were able to actually nail it down for sure. But the calculus approach was more general. The calculus approach said, you know what, let's not even think about a circle. Let's just think about a function in general. Just any function. Call it f. That's definitely not straight lines, right? This is curved. Let's imagine that you drop down to some point on the x-axis A, some other point here B. This shape in here, excuse me, I'm not sick, I don't have COVID, I just sound like shit. This shape in here, right, is definitely complicated, like a circle, right? It's got curves in it. So you could argue that that's even worse, right, than this. If we could find the area of that, then it should be easy to find the area of this, because all we would have to do is graph like a half circle, right? If we could graph like a half circle, which we know how to graph a half circle. If we could graph a half circle, we do know how to graph a half circle, right? We know the equation of a circle. We'll get to it later. If we could find the area of this, right, then that's half of what we're looking for, right? So that's more general, understand? This is the way we wanted to attack it. Say, can you just look at a general function and find the area underneath it? Got it? So if this is the area, what is it, right? So we started with kind of like a method of exhaustion. And what we're going to do right now is we're going to pick a function right now, and we're going to try to estimate the area underneath it and see how it goes. And we're going to do it the way that they did it back in the day. It's called Riemann sums. I'll put this on the board later. So as a specific example, we're going to take the function f of x equals x squared on the interval, let's go 1 to 5. That says take f of x equals x squared on the interval 1 to 5, and let's approximate the area. Let's see if we can figure out the area. So I'm going to draw the function first. We all know what x squared looks like, I hope. Yes, yes. Okay, and we're only going to go from 1 to 5, so from 1 to 5, and imagine, well, I'll do it in purple. Imagine we do this. What we want is that, right? I want that area. So here's my first attempt, right? To approximate this, here's my first attempt. You tell me if you like this idea or not. First attempt. What I'm going to do is I'm going to take that picture. All right, I'm going to take this region here. And to approximate that, what I'm going to do, I don't think I have a good red one here. No, I'll use blue. What I'm going to do is I'm going to approximate this with a rectangle, because I know the areas of rectangles. So I'm going to take a rectangle that goes from this point over, down, over, and there. There's a rectangle. Do we know the area of that rectangle? What's the area of this blue rectangle? Do you know how wide it is? So that blue rectangle has a width of 5 minus 1, which is 4, right? And do you know how tall it is? 25. How do you know it's 25? Because I picked that top right corner, didn't I? To be the top of my rectangle. And that 5 gets plugged into the function, x squared. 5 squared is 25, right? So this distance from here to here is 25. So what is the area of this rectangle? 100. So the area of this is 100. So what I'm telling you is that this purple area right there, whatever that is approximately 100. Do you like that estimation, or do you think that estimation sucks? It's a little bit extreme, isn't it? Like, do y'all see how much error I have from the picture? Like, I counted all this area, including this, right? But that's not part of the area I'm interested in. So I have too much error here. Would you agree? How could I get a better estimate? Break it up in maybe a couple of rectangles, right? Instead of one big one, yes.
You can also do like a trapezoid.
You could do another shape, right? Something else. I'm going to stick to rectangles because at the end of the day, it doesn't matter what shape you use. It's going to get you to the correct answer. So here's my second attempt. Second attempt. So in my first attempt, what I did was one rectangle, right? And in my second attempt, I'm going to go with 2 rectangles. So I do the same picture. Here's my parabola. Here's 1. Here's 5. I'm trying to figure out the area underneath this thing. All right, where should if I'm going to do 2 rectangles, I should do 2 equal widths, right? The rectangle should have equal width. So how about we cut it right here at what, 3? That makes sense to you? To cut that at 3? And then to make the first rectangle go up to that top corner, over and down. And then the second rectangle go up, that corner down. Do you all see that this would be better than this? Yeah? Y'all can you see it in here? It would be this, wouldn't it? And so what we've done is we've eliminated that error, haven't we? Now we still have error, don't we? But we've eliminated some of it. So now we have 2 rectangles. Let's look at let's look at rectangle 1. I'm going to call it R1, R sub 1. Can you tell me how wide R sub 1 is? This is R sub 1. It's too wide, isn't it? 3 minus 1, so too wide. How tall is it? 9. You're getting that from plugging in 3 into the function, squaring it, getting 9, right? Okay, so what's the area of rectangle 1? 2 times 9. I'm going to do it the other way. I'm going to do 9 times 2, which is 18, yes? The area of rectangle 1 is the height times the width, 18. Now I also need rectangle 2, right? Rectangle 2, these are not drawn to scale, obviously, has a width of 2. How tall is it? 25, because you're using the right endpoint. And so the area of rectangle 2 would be 25 times 2, which is 50. And then our approximate area then would be those two added up, right? So the area would be approximately area of rectangle 1 plus area of rectangle 2, which is, 18 plus 50, which is 68. This is hard. My throat's so dry. Sorry, everyone. Better approximation? 100 now to 68. What would be even better? More rectangles, right? Right? Yes.
So, kind of, I'm starting to notice, in here, we could use that sum of application you showed us earlier and use that so that we could say A is equal to the sum, or the sum of A is equal through the number N, which.
Right here, I'm kind of alluding to it right here. Do you see how we're adding up rectangle 1 and 2 as area? What if we had 3, 4, 5? Sigma would be a better condensed notation. So I could do this now. My third attempt, right? I could do 3 rectangles maybe. Fourth attempt, 4 rectangles, right? 5 rectangles, 6 rectangles. Better, better, better. So maybe I should start thinking about what it would be to add up n rectangles. Right? Maybe we can come up with a formula for n rectangles. I think I'm ready to jump right to that. I feel like y'all are ready for it. So on our third attempt, we feel ambitious. We're going to go with n rectangles. Now you have to pay attention here. This is very important, all right, to understand this conceptually. Here's my graph. Here's 1. Here's 5, right? There's n rectangles in here, right? There's n of them. So if I draw them, you can't really tell me how wide they are yet, but imagine there's a bunch of them in here. Right? Let's look at rectangle 1. Let's look at rectangle 1 over here. Rectangle 1, how wide is it? We're going to make them equal width, exactly. So, okay, back when we had 1 rectangle, how wide was it? Not 5, it was 4, right? It was 5 minus 1. 4. When we had 2 rectangles, we had, each one was 2, right? How is that related? It's 4, okay, so good. So we had one rectangle here, right? 1 rectangle. The distance from here to here is 4, isn't it? This distance from here to here is 4, always. If we use 1 rectangle, then 4 divided by 1 is 4. If we have a distance here of 4, and we do 2 rectangles, then 4 divided by 2 would be 2. If we have 3 rectangles, then 4 divided by 3 would be 4/3, right? If we had 4 rectangles, then 4 divided by 4 would be 1. It'd each be 1 wide. So if we have n rectangles, each one would be 4 over n, right? The width of this would be 4 over n. Questions? It's the distance from here to here, right? The distance from here to here divided by how many rectangles you have. How tall is it? This is the part that gets people. How tall is it? Well, in order to tell you how tall that is, I have to tell you where I am. And I'm right here at this. I'm right here at this first right endpoint right there. Can y'all tell me where that is? Exactly. Very good. This is 1 plus 4 over n. Very good. So this is 1, right? And I've added to it one little width of a rectangle. So that's 1 plus the width of one rectangle. That's where I am, right? I don't know what that number is. I don't know exactly what that number is because I'm using n rectangles.
The length would be that squared.
It would be that squared. So wouldn't this be the function evaluated at 1 plus 4 over n? Isn't that how tall it would be? Which would just be take this and square it, yes? I'm not going to write that. I'm just going to write the function evaluated there, which in this case, the function I erased it was x squared. Do y'all agree? So the area of rectangle 1 is the function evaluated at 1 plus 4 over n times 4 over n. That's how tall it is. That's how wide it is. Yeah? How about rectangle 2? For rectangle 2, how wide is it?
1 plus 2 times 4.
Just the width. Just the width. It's 4 over n still, right? They all have the same width, don't they? They all have the same width. 4 over n. The height, though, is different because now, I wish I had red. Now you are at the second point, right? You're now here. There's a lot of different ways I could write that point, right? I'm going to write it this way. It's 1 plus 2 jumps. 2 of those jumps, right? So I'm going to put 2 times 4 over n. You start at 1. To figure out what this point is, what you do is you start at 1 and then add to it 2 jumps of 4 over n. This one was 1 plus how many jumps? 1 jump of 4 over n. Understand? So this height would be the function evaluated at 1 plus 2 jumps of 4 over n, which would just mean for this function that I square that, right? So the area of rectangle 2 equals the function evaluated at 1 plus 2 jumps of 4 over n times 4 over n. We're starting, hopefully, to see a pattern. Any guess as to what the area of the third one would be? Well, how wide would the third one be? 4 over n still. How tall would it be? Well, we need to know that point, right? That point would be 1 plus 3 jumps, right? 3 jumps of 4 over n. So I would put f 1 plus 3 jumps of 4 over n times 4 over n. Yes? What would the, no, let's not do dot dot yet. Let's do the area of the fourth rectangle would be f of 1 plus 4 jumps, right? 4 jumps of 4 over n times 4 over n. And so on and so forth, right? Until I got to the last one, dot, dot, dot. What's the area of the nth rectangle? Well, that would be f of 1 plus how many jumps? N jumps, right? N jumps. N jumps of 4 over n times 4 over n. Wait a minute, shouldn't that be the right endpoint? Shouldn't that be this very right endpoint when we get to here? So shouldn't that be 5? Is it? Ends cancel, 1 plus 4 is 5. So that is the right endpoint. Okay, got it? Now watch this. So basically, the area, right, that I'm looking for is all of those added up, right? It's all of those added up. So it's the sum, k equals 1 to n of all of the areas of the rectangles. It's area of rectangle 1 plus area of rectangle 2 plus area of rectangle 3 plus area of rectangle 4, all of them together, right? In all these formulas, what's the only thing changing?
The number multiplied by 4.
The number of jumps. Everything else is exactly the same. Do y'all see that? There's a 1 in front of this, right? 2, 3, 4. Everything else is exactly the same in the formula, right? All the way till you get to n. Yes? So this equals sum k equals 1 to n f of 1 plus what? K times 4 over n, all of that times 4 over n. I'm going to change the color of the k. Right? That's the only thing that's changing in these formulas. So when I let k be 1, I get this first one, right? Then I say plus, and now k is 2, this one, then plus, now I let k be 3, this one. That's going to add up all these areas, isn't it? Yeah? Okay, how am I doing on time? All right. So, do we know what this is? Do we know what this is right here? Do we know what it is? Well, do we know the function? Did I give you the function? F of x is x squared. So f of this, isn't that just square that? Okay, here's where the fun begins. Well, the fun, we've been having fun already, but now the real fun. Let's, for this particular function, right? Don't forget, we're using f of x equals x squared. Is the function we're looking at. So that sum becomes sum k equals 1 to n. All I'm going to do is take the 1 plus k times 4 over n and square it, and then I still have 4 over n. So this piece right here, I'm plugging this right here into the original function, right? That's getting plugged into the function. So what do I do when I plug that in? I just square it. Now, algebra. Let's do some algebra here. Can you square that? Yeah, let's do it on the side here. I'm going to look at it a little different. I'm going to write it as 4k over n squared times itself. Right, so that's what it would mean to square that. So let's FOIL it. You get 1 plus, you get 4k over n, and then another 4k over n. You add those together. You should get 8k over n. And then plus the last term, 4k over n times 4k over n, 16k squared over n squared. Right? Isn't that what I would get? Okay, that goes here. Sum k equals 1 to n of that 1 plus 8k over n plus 16k squared over n squared, and then I still have out here 4 over n. We're getting there. I'm going to distribute the 4 over n through. I'll do that over here. So we are now at sum k equals 1 to n. Where are we? 4 over n, right? 4 over n, that's what we get there? Yes? And then we get what? 32k over n squared. And there's a plus sign there, right? So can I split this into another sum? Plus sum k equals 1 to n. You said it was 32k over n squared, right? And then I have another sum k equals 1 to n of 64k squared over n cubed, right? Y'all follow me? All right. Real important point right now. N in this problem is a constant, right? N was the number of rectangles. So it's a fixed constant. The only thing that's changing in these summations is the k's, right? So the 32 is a constant, and that n squared is a constant. The 64 is a constant, the n cubed is a constant. The 4 over n is a constant. So I'm going to use, on this first sum, I'm going to use the property, this property. Sum k equals 1 to n of a constant. What was the answer to that? Constant times n. So what's this times that? 4, right? The n's cancel. So that's just a 4. Plus, on this one, I'm going to pull the 32 over n squared out of the sum. And then here, I have k equals 1 to n of just k. That is a formula I gave you a minute ago. Plus, this one is 64 over n cubed, and then times sum. Whoa, holy moly. That sum got out of control. Sum k equals 1 to n of just k squared, yeah? So you have formulas for this. These are called Riemann sums, what we're doing right now. I'm not going to require you do this, all right? But me going through all this, you are going to appreciate the theorem we're going to have in a little while, okay? Because then the theorem's going to make it we don't have to do this. 4 plus, okay, 32 over n squared. What is that middle sum that I circled there? The sum k equals 1 to n of k? N times n plus 1 over 2. Okay, plus 64 over n cubed. And then the squared one is n times n plus 1 over 2n plus 1 over 6. There it is. That formula will give you an approximate area. All you have to do is provide me n now. That's it, right? Yes?
On the first one, the 4 over n,
No?
the n canceled. No, on the other side. On the other side. Where it equals 4.
Here?
Yes.
Yeah, yeah. The n's canceled.
The n's canceled. On the next one, the 32 over n squared, you don't lose an n?
No, because this property that I gave you here is only if we're adding up a constant. Just a constant. A constant here, and that's all we have. Here, we have a constant